Okay, so last lesson we looked at what an exothermic reaction and an endothermic reaction was, and looked at this in terms of energy level diagrams. What we're going to do now is actually calculate the energy changes during reactions. And we're going to do this using things called bond energies. Now, if you want to rearrange atoms from how they are in the reactants to products, we need to break some bonds, and we then need to make some bonds to form our products. And we can use these things called bond energies, which is the amount of energy required to break 1 mole of any bond. So we're going to start off with an example of hydrogen burning in oxygen. Now you can do this on rough paper along with me, or you can follow the slides on the PowerPoint doing the same idea, but you don't need to draw this one down in your books. So we're going to have a look at hydrogen burning in oxygen. And so what we always need to start off with is a balanced equation. So if we've got hydrogen and, oops, let me move you around a bit so you can see that more clearly. We've got hydrogen burning in oxygen to give us water. Okay, 2 O's on the left, so we need 2 waters, 4 H's on the right, so we need 2 H's. Now, I'm going to make my molecules out of the Play-Doh. You can do this as well if you manage to find some. So we've got 1 hydrogen molecule there and another hydrogen molecule here. And they're going to react with oxygen. Now, if you remember with oxygen, oxygen's got 6 electrons in its outer shell. So it needs to share 2 electrons. Hang on, let me just do this bit again. It needs to share 2 electrons in order to fill up its outer shell. So we need a double bond. So we've got hydrogen and we've got oxygen there. And we can use our bond energies then to work out how much energy is going to be needed to break all of those bonds. And you will always be given the data for this, so it's not something you need to remember at all. So we can look up, first of all, we need to look at what bonds we've got here. So we've got 2 hydrogen-hydrogen bonds, and we've got 1 oxygen-oxygen double bond. We need to remember it's double. And we look up the values for the bond energies. And so hydrogen-hydrogen bond is 436. So we've got 2 lots of 436 kilojoules, and an oxygen-oxygen double bond is 496. And if we add up all of those, we get 1,368 kilojoules. So that's how much energy it's going to take to break all the bonds in the reactants. Now, if we're going to want to make our products, we're going to put in that 1,368 kilojoules. So I'm breaking all my bonds there. And then we need to rearrange these atoms now to make our products. So 2 lots of water. So I am going to bond these together so we can now form some water. There's 1 water. And here is my other water molecule here. Okay, so we've formed bonds here, and we have formed 4 OH bonds. So this value over here was our reactants. Always a good idea to have a bit of annotation. And over here, we've now got 4 OH bonds. Okay, so that is 4 times 463, which gives us 1852 kilojoules for our, let's move it across there, for our products. Okay, now we could think in terms, so that's the amount of energy needed to break the bonds in the products. So we can think of this in terms of an energy level diagram now. So I'm just going to move this up a little bit. So if we were to start with our reactants over here, so this is our hydrogen and our oxygen, we needed to put in 1,368 kilojoules in order to break everything up into atoms. And for our products, to break them up into atoms, we needed to put in 1,852. So our products, I should have given myself a bit more space here, are going to be down here. So bond energies is all about breaking bonds. So looking at this, if we want to work out what this little difference is in here, what we need to do is do our reactant bond energies And then we need to go the opposite direction to this. So we do minus our product bond energies. So what we can say overall then is that our energy change, remember delta H, delta for change, H for the energy, is equal to our reactant bonds minus our product bonds. Okay, let me just get myself a little bit more paper out here. This is where we need our nice rolly boards in the labs. Okay, so we can then just come and have a look at the numbers we've got. So delta H for this reaction, our reactant bonds was 1368, our product bonds was 1852, and so our overall energy change is then going to be minus 484 kilojoules per mole, like that. Then we need to think, is this exothermic or endothermic? So we look at the sign. Our sign is negative, and so that means that this reaction is going to be exothermic.